Okay, so now we're going to talk about the traction vector components. All right, and so to recap, we have our mechanics potato. We've taken an imaginary slice through that potato so that we will have something that looks something like that. And on the top surface of our potato, we have some internal forces which are needed to keep our potato in equilibrium with the external forces that are acting on it here. And what we've then done is we've said, okay, we're going to take a little tiny patch of potato and we're going to look at the internal forces on that patch. So that we're going to come over here and we're going to see that patch. And if we take all of the internal forces over that square, we can compute a resultant force vector, which we call delta F with a squiggly because it's a vector. And that's our resultant force. And you can remember the area that we're considering is of area delta A. Now, I talked a little bit about how we've chosen a particular slice. So we've looked at a slice going this way. We could have just as easily have taken a slice the other way. So that would be straight down or any angle in between. And whenever we pick a plane to slice, we need to determine how we can orient that plane in space. And if you can remember, if we go back to sort of our definition of a plane in 3D space, the way that we do that is with a normal vector. And I'm going to use a unit normal, which would be why I'm giving it that hat notation. So it's just a vector that's perpendicular to our cut, wherever that cut may be. And so as soon as you start to make these slices, now you have a normal vector. You might ask yourself, okay, I have a resultant force. I should determine what the components of that resultant force are in terms of a vector perpendicular to my cut or my plane and in the plane. So the tangential component to that resultant force. And that has to do with the two ways that things typically break. Either we pull them apart or we crush them, or sometimes we're actually shearing these two pieces and causing a failure. So if you're thinking about takeaways, things that you want to know about, you want to know what's the axial stress on a component to see if it breaks in tension, and you want to know what the tangential component is to see if we fracture that thing by shearing. And what we're going to do is define those components. So you can imagine this is in the direction of n, and we can project our resultant force back. And this component here, we're going to call delta Fn, n for normal. Now, if we take another projection, if we project our resultant force delta F down into the plane, we'll have another component down here, which I'm going to call delta Ft for tangential. And you can see that our resultant force is just the sum of those two vectors. So just to write all of these down, delta F squiggle, the vector, is the resultant force vector. And hat, that's the unit normal that describes the cutting plane, we have delta Fn with another squiggle, it's a vector, which is the normal component of delta F. And we have delta Ft, which is the tangential component of delta F. Okay, and so now if we know our resultant force, the question is, how do we determine these components? So now we're just going to look at the magnitudes. So the normal component magnitude, if we wanted to know what that was, all we'd have to do, so that I'm going to call this delta Fn, no squiggle, that's going to be equal to delta F with the squiggle, that's the vector dotted into that normal vector. Okay, and that's going to give us a value, which would be the magnitude of the component in the normal direction. And now we're going to make another definition here, and we're going to say that if we want to look at the normal stress on this cut in this location, that's going to be a sigma, sorry about that, and that's going to be equal to the limit as delta A goes to 0 of delta Fn, so the magnitude of the normal resultant vector, divided by delta A. And that is going to be equal to the traction vector, which we defined in the previous video, dotted with the unit normal vector. So I'm going to box around that. That's important. That's how we compute our normal stress. And you can see that it's very similar to what we did when we looked at 1D, right? This is just force divided by an area. What's new, of course, is that we have now some other components because we're in 3D. So we have this tangential component. And the tricky part is if you go back to our potato, our tangential component could be at any orientation. So we don't have a nice vector like we did for our normal component. So we're going to have to do something else. But if we just want to know the magnitude, so delta Ft, the magnitude, all we have to do is use our Pythagorean theorem, and we can say that the square root of delta F squared, so that's the magnitude of the resultant force vector squared, minus delta Fn squared, so that would be the magnitude of the normal component vector squared, is going to give us the magnitude of the tangential component. So there you go. Now we have a value, and if we want to know what the tangential stress is, the magnitude, we're going to give that another name. We're going to call it tau for tangential, and that's going to be equal to the limit as delta A goes to 0 of delta Ft over delta A, and that's going to be equal to the square root of the magnitude of the traction vector squared minus the magnitude of the normal stress squared. And there you have it. So now, if we can determine the traction vector, so t, at a location, we can compute the normal stress and the tangential stress. And if we want to turn those into vectors, so this would be the normal stress vector, that's just equal to the value. So it just scales the normal unit vector. And we could also find the tangential stress vector, tau, and that would be equal to the traction vector t minus sigma. sorry about that. Hopefully you guys can see that now. Here's the normal stress vector. Here is the tangential stress vector.